Hi guys, welcome back to Data Every Day. Today we're looking at a data set of hotel guest purchases, I assume, or like stays at a hotel, and we're going to try to predict which hotel it is between these two hotels. One is a resort hotel and one's a city hotel, based on a series of features, such as when they arrived, how many adults, children, and babies came, what kind of meal, and so on. So let's get into it. I have the task for today, which is given data about guests at two different hotels, one city hotel and one resort hotel. Let's try to predict which hotel a guest is staying at. So you can see I have imported the standard libraries, NumPy, Pandas, Matplotlib, Seaborn, and Plotly Express. These last three for data visualization. And then for pre-processing, we have label encoder, standard scalar, and train test split function from sklearn. And then for actually building our model, we'll be using a TensorFlow artificial neural network to make our predictions. So we can start by reading in our data. So we'll call it data, using the pandas read CSV function. And we'll take in a file path. We can actually get the data over here. And we can get this CSV file, the file path right here, copy file path, paste it in, and then check it out. And you can see right away we have this ... here, which means we're not seeing all the columns. I think there's a maximum of columns that pandas will display. We can override that by going to the console, typing pandas.set option, max columns, none. Alright, now if we load this up, you can see we no longer have the ... and we can see all of the columns. So we have a good number of features here, 32, and this first one is the one we're trying to predict. So now the question becomes, well, where do we start? So I'm going to start by getting a little preliminary information on the dataset, and you can see most of these columns do not have any nulls, but there are a few down here that do. In addition, we have a good mixture of numerical and text columns. So let's start pre-processing. And I'll start by checking out the null values. So I'm summing all the... So isNA gives us a true-false data frame where we'll only have a true value where there's a null value. So if we sum across the rows, we'll get the total number of nulls in each column. Very similar to what we had up here, but now we can actually see explicitly we have a few nulls here, a few nulls here, a decent number here, but then here we have way too many, right? Because look, our total number of rows is 119,000, and this one has 112,000 nulls. So that column is virtually useless to us, because if we were to impute the other values using the mean of what we do have, there's just not enough data there to give us accurate results. So we're just going to drop that one. So data.drop, it's called company, axis 1. And we're going to make that data. And then what else we have? So we're left with these three: agent, country, and children. And so we can impute the missing values of numerical columns with the means of the data that is in those columns, right? So we got to see how many of these are numerical. So we have children, country, and agent. So if we go up here, we'll see children. Here's children. This is numerical. So children we can do. Country, this is not numerical. Those are text values. So we can't do country for imputing means. And then the last one was agent, and that is also numerical. So what we'll do is say, okay, we have this children and agent, right? Those are the two we can do mean imputing on. And so for column in those two, so for each one, we're going to say that column is now going to be the same column but with the NA values filled. So fill NA will fill null values with a given value, and the value we'll give it is just going to be the mean of the column. Alright, run that. We take another look at this. Now we only are left with this country with null values. And because it's a nominal feature, so that means it takes on more than 2 values, and it has no inherent ordering in the values. Because of that, we'll be using one-hot encoding to encode it. And the beauty of one-hot encoding is that we don't have to worry about null values because they'll automatically be taken care of by the encoding. So we're essentially done with null values now. And we can move on to encoding. Alright, so before we start, I'm going to make this function that we will use a few times called get categorical uniques, and it's going to take in a data frame. It's just going to return a dictionary that maps a column name to a list of the unique values in that column. So it's mapping the column name to the unique values of that column turned into a list. And that's for every column in data.columns. Not data, sorry, df. But only if the data type of that column is object. So this is going to give us the unique values of each column that has categorical data. So if I call that on our data, you can see we now have a list of each categorical variable and all the unique values that are stored in that variable. This is a very useful function. Alright, so we're going to have to encode these one by one, or at least separate them into different categories for encoding. So there's 3 types of encoding. Well, there's ordinal encoding, which we would encode values in a given order. There's one-hot encoding that we would use for values that do not take on a given order. And then you could consider the last type as binary encoding, which is sort of like a variant on one-hot encoding, but that's just give it 0 or 1. And that's only if it takes 2 values. So what I'm going to do is I'm going to categorize all these features. But before I do that, let's just look through. So we have, this is definitely nominal, right? A bunch of these are nominal. They have just a bunch of values that don't take on an order. And yeah, it looks pretty good. And oh, looks like we have a date. So the date one, I'm going to process first. The reason for that is, well, we're not going to encode it as it is. We want to make 2 new features out of it, year and month. So what I'm going to do is, so this is called reservation status date, right? If I apply a lambda function to that column that takes in some x, so an x looks like this, and we're going to turn x into x evaluated from 0 to 4, so indexed at 0 to 4, and that will be turned into an int. Then that looks like just the year, but as an integer. So this can be our new column, which would be reservation year. So that's what I'll do. I'll say data sub reservation year equals this. So we're extracting a new feature from this date feature. And I'm going to do the same thing for the month. However, this will be reservation month. And over here, instead of indexing from 0 to 4, which will just be the first 4 characters, we're going to go, so this is 4, this is 5, so we go from 5 to 6, 7. So 5 to 7. 5 to 7. And if we want to take a look at what that looks like, we can just run this particular block, and you can see now the months like these, right? 7, 7, 5, 4, 6 have been converted. And so we'll set that, and when we're done, we're going to drop the original reservation status date, like that. and from axis 1. Alright, so that has effectively processed our date columns. If we now take a look at data, you can see at the end before we had this date column, now we have a year and a month, which is much more easy to use, and now it actually doesn't need to be encoded. That essentially took care of the encoding as well because it's already in numerical form. Alright, so what can we do next? Okay, why don't we get the categorical uniques again? So this is that function we made, and now we can see it without those dates clocking it up. Alright, and now what we'll do is we'll separate. So first we'll have the target column, and that's going to be, I think it's called hotel, right? Hotel. This is what we're trying to predict. Then we're going to have binary features, ordinal features, and nominal features. So we're going to go through this one by one and figure out what type is each feature. So arrival date month, that's ordinal because it goes. You can assign an order to the months. If we started with January as 0 and end with December as 11, that would give us a variable that says when we have very low or very high value, that's a cold month, and when we have like a medium value, that's a hot month. So that you can consider that as ordinal. It's sort of a measure of temperature and climate changes. So I'll throw that in here, ordinal features. Then we have meal. So this is definitely going to be one hot encoded. And you notice we have this undefined value. So that's essentially a null value. So the good thing about one hot encoding is that you don't have to make a new value for null values. A new column for null values. You can just put an example that has an undefined value there. You just have all zeros for the one hot columns. So what we'll do is actually convert that. We'll say data sub meal dot replace undefined with numpy.nan, and that should work. Alright, so if I say data sub meal equals that, if we take another look, you can see now it's nan. Fantastic. So meal is going to be nominal. Alright, country. This is also going to be nominal because there's no ordering between them. Alright, then we have market segment. This is nominal as well. Distribution channel, also nominal. Reserved room type, also nominal. So it looks like we have quite a few nominal features. Assigned room type, also nominal. And we have deposit type, customer type, and reservation type status, and I think those are all nominal as well. So it looks like we have only one ordinal feature and no binary features, and everything else is nominal. So I'll just remove that, and now this makes our jobs actually pretty easy because we only have to use one function to encode all of these different columns. So let's deal with the ordinal feature first. So I don't have to make a function for this because we're only going to run it once, but essentially we're going to have a month ordering, and we've got to see what kind of values do the months take. They're full names of months. So what I'm going to do is make this list, January through December, January, February, and I'm not going to type it out, I have it right here, so you can see January, February, March, April, May, June, July, August, September, October, November, December. Then what we're going to do is apply a lambda function to the reservation month. No, sorry, it's arrival date month column. And the lambda function is going to take in some x, which would be one of these months, and it's going to return that month indexed in month ordering. So let's say we have March. Let's say X is March. Okay, we're going to take this thing and index it at March. So it's going to go through here and find March, and because this is a list, it retains order. This has an index, so this is 0, 1, 2. So March will become 2. If we had May, that would become 4. June would be 5, and so on. So basically what we're doing is just turning these into numbers based on what time of year they arrive in. So I'm going to set the month column equal to that. And now we should only have nominal columns remaining. Now I think this is a good chance to visualize our data and see if there are any like extremely high correlations between columns. Because if there are, then we have redundant features. So let's say visualizing correlations. So we only want to visualize the numerical columns. So let's make a list of numerical columns. That will just be a list of columns for every column in data.columns if data.dtypes subcolumn is not equal to object. So essentially this is all numerical columns. Then we're going to create this correlation matrix, which will just be data sub numerical columns dot core. That's a pandas function that returns the correlation matrix from the data frame. And then we're going to use Seaborn to generate a heat map of the correlations. So set up a new matplotlib figure here. Fig size is going to be 18 by 15. SNS.heatmap core. We're turning on annotations. So we're making a heat map of correlation of core, right? Turning on annotations so we can see the actual correlation values. We're going to specify our min and max values for correlation. And let's give it a nice color map, Mako. Then plt.show. Alright, so this is all of our correlations. And one thing we notice immediately is that almost all of the variables are uncorrelated. So they all have values very close to 0, like huge chunks of just blue. But then we all have these little pockets where something is happening. So in the case of reservation month and reservation year down here, you can see we have a slight negative correlation. And this makes a lot of sense because, well, actually, I'm not sure about the year and month being correlated. That is interesting. This is suggesting that when we have when the year, like if we're later in the years, people tend to go earlier in the year. That's interesting. But you know, it's not really of much consequence because it's not like extremely strong. It's negative 0.5. So we're just looking for ones that are like really strong here. And you can see we actually have one here. This is a 1. So what that means is the columns are literally identical. If a correlation of 1 means there's absolutely no difference between the columns. So arrival date week number and arrival date month are the same. We can verify that. Look at data. Arrival date week number. Where's that one? This one, 2735. And then arrival date month was the other one? This. So they're not actually the same value, but they go up at exactly the same rate. So every time we have a 6, we have a 27. Every time we have a 7, we have a 35. And so on. It's very interesting. But what that means is we can just drop it because it's not conveying any more information. So arrival date week number, let's just drop data.drop arrival date week number. And we want to see, is there any others we need to drop? And this one catches my eye here, 0.93. This is also extremely high. It's saying whenever we have a high reservation year, we also have a high arrival date year. And that makes sense because not many people are going to make reservations outside of the year which they plan to stay. So we can drop we'll drop reservation year as well. Alright, so enclose that in the list. And we're dropping it from the column axis. Alright, so if we took one more look at this, should be able to see those high correlations are gone, and now we're left with pretty moderate correlations, and should be good. This should be a good set of features to use. We do have to one-hot encode all those other columns though, so we're going to say back to encoding. Alright, so we have this data, and most of our stuff is in numerical form now, but we have these text values that need to be converted. So we're going to make a function called one-hot-encode. It's going to take in a data frame, a column, and a prefix to encode that column with. And it's going to start by making a copy of the data frame. Then we're going to create a dummies matrix using pandas.getDummies function. We're creating it from the column of our data frame, along with a prefix that we specify. So dummies will just make a bunch of columns for each unique value, where we'll get a 1 or a 0 depending on whether that particular column. Here, let me just, it's hard to explain. Let me, I actually forgot the parentheses here. Wait, no, never mind. Okay. Let me just show you. So we have data sub. Let's use hotel. So what this does is it takes the old values, right, and is making new columns with them, and then it's creating a 0 or a 1 depending on whether that example had which one it had. So this one had resort hotel, so we have a 1 there, and a 0 would have in all of their columns. Alright, so I'm making that dummies matrix, and we're going to put a prefix, so the column names will have a prefix attached to them. That's just to prevent duplicates, and so that we know where the one-hot columns are coming from. And then we're going to concatenate, so we're using pandas.concat, two data frames, the original data frame and the new dummies data frame, along the first axis, axis 1 for column axis. And then we're going to drop the original column. Alright, and then we'll just return the data frame. So now, let's look back at our list of nominal features. Where is it? Here, nominal features. And I'm not going to actually run this code, but I just want to look at it. What we need to do is give a list of prefixes to use for each of one of these. So we'll call it one-hot prefixes. And let's just start making them. So meal we can say is M, country can be C, market segment can be MS, distribution channel can be DC, reserved room type, we can make it RT for reserved type, and we have assigned room type can be AT, deposit type DT, customer type CT, and reservation status RS. And now we can just remove this. These are our prefixes. Now what we're going to do is for each column and prefix, it's going to be a column prefix pair given by zipping together the nominal features and the one-hot prefixes. So it's going to zip them into tuples and then iterate through one by one each tuple at a time so that we can process both values at the same time. And then data will equal one-hot encode data, the column, and the prefix. And simple as that. Run that. And we'll take another look at our data, and we can see that all of those text features have been converted to one-hot features. And you can see up here the prefixes are on the columns. So what that means is we are fully ready to scale and train, except I just realized we actually have to encode the label column, which we can just do simply using sklearn's label encoder. So data sub hotel equals label encoder dot fit transform data sub hotel. And let's say we want to, so we'll do that, and let's say we want to know, well, is resort hotel 1 or is resort hotel 0? So then we can make a dictionary that maps an index to a label for every index label pair in enumerate label encoder dot classes. So this is a list of the classes. Sorry, there's an underscore there. This is a list of the classes in the order they were encoded. So by enumerating it, we can get the actual new values. So you can see city hotel has been mapped to 0, resort hotel has been mapped to 1. So if we look at data, you can see now hotel is in 1-0 form, which means we're ready to split and scale. So let's split into x and y. So y is going to be a slice of our data frame, all rows and just the target column, which would be hotel. Then x is going to be data.drop the target column. We're dropping it from axis 1. So y would look like this, 1s and 0s for just the hotel, and x will be everything except the hotel column at the beginning. Alright, then we'll make a scalar. And this will be the standard scalar from sklearn. Just going to give each column mean 0 and variance 1. And then x is going to be scalar.fitTransform x. And that's it. X will no longer be a data frame, but we can see all the values take on values near 0. Alright, and then we'll split into train and test sets for training using the train test split function from sklearn. Xtrain xtest, ytrain ytest equals train test split xy. We'll give it a train size of 70%, and we'll include a random state so we can reproduce the results. How about 46? Okay, then we're ready to, we'll say modeling and training. So let's take a look at the shape of our input. We have 119,000 examples and 246 features. So we're going to set up a TensorFlow neural network, and we're just going to use the classic architecture that works very well with tabular data. Especially neural networks work really well when you have a high number of features and when you have a bunch of one-hot columns like this. Wait, what is this? Where's our one-hot columns? Just take a look over here. All these one-hot columns. Neural networks excel with this. So we're going to include the shape is going to be a vector of length 246 for each example. And then we'll make a dense layer. So we're going to make two hidden layers, both dense, and both are going to have 64 activations and a ReLU activation function. So we pass in inputs here, and we make another one, but pass in x on the second one. Then we will make an output layer, which is just another dense layer, but will output only one value, and it will have an activation of sigmoid, so that we get a probability estimate for the positive class, which was resort hotel. So essentially what we're outputting is the probability of a hotel being a resort hotel. Alright, and we're passing in x here as well. Then we make our model, tf.keras.model. We pass in inputs and outputs, so this and this, these two. And then we're going to compile our model. So we need an optimizer. We use Atom. We need a loss function, binary cross entropy, and a metrics. Let's see something. So note that y is just this length, this vector of 1s and 0s. So if we sum across y, we'll get the total number of ones. And if we were to take the mean of y, we would get the percentage of ones in y. So by getting the mean, we're essentially saying how skewed are our classes. And you can see, so 33.5% of the data is positively labeled. So we don't actually have a perfect 50-50 balance of Hotel 1 and Hotel 2. So we're not going to just use accuracy. We can use accuracy, but we're also going to include the area under the curve. So tf.character.metrics.auc. So this metric is extremely good. It's the area under the receiver operating characteristic curve. It's extremely good when you have skewed classes because it takes into account performance within each class, but it also takes into account performance across classification thresholds. So in this case, we don't care about the classification threshold. So what that means, are we classifying at 50%? So if we have a greater than 50% probability, are we classifying as y equals 1? Or we could move that up to 70%. Are we classifying y equals 1 only if the probability is over 70%? In this case, it's not so important, but let's say you had a example where you really wanted an anomaly detection or something. You really wanted to know performance within a very small class, and the threshold had to be very close to one side. Then you would use maybe the F1 score or another metric. But in this case, AUC will work very well. So we're going to use those two metrics, and then we're going to create say batch size will be 32, and we'll train for 10 epochs. So we're going to fit our model and store it in the history object. Actually, history variable here. And we're going to train it, fit it on xtrain, ytrain. And we're going to give it a validation split of 20% and pass in the batch size and the number of epochs. Alright, and we'll train. And this should be metrics, not metric. Alright, it's going already, looking very promising. Let's start plotting the results while it trains. So we'll use Plotly Express to generate a line chart. And we're going to draw values from history.history. So this is our history variable, and that actually has a dictionary called history, which we will draw two values to plot on the y, loss and val loss. So it's a dictionary that maps loss to all the losses across the epochs, right here, and val loss will be mapped to all the validation losses across the epochs. Then we can give it some labels. On the x we'll have epoch, and on the y we'll have loss, and we'll give it a title, loss over time. Alright, this is finished training. Let's take a look. Oh, I didn't show it. Fig.show. And this looks pretty good. Let's see, what was the lowest validation loss so far? I could train for longer, but I think this it starts to go back up after this. I was experimenting before. So we're going to find the argmin of history.history subval loss. So min would give us the lowest value, but the argmin will give us the epoch at which we find the lowest value, and epoch 6. So since this starts from 7, if I want to stop training at the optimal epoch, we're going to train for 7 epochs. Sorry, it starts at 0. Did I say 7? It starts at 0, goes up to 6. That's 7 epochs in total. So we'll train for 7 epochs. Try this again, just so we can try to get the maximum performance that we can. And then when we're done, we will do model.evaluate x test, y test. So this is evaluating on the test set, which is completely unseen data up to this point. And we're almost there. Let's give it 1 second. Alright, it's completed. Take a look at the chart again. It has converged. Looks like 5 or so. Yeah, it's gone down by 1. Whatever. It's fine. Take a look at the evaluation, and we get extremely good results. This is an AUC of 0.99, so it's really almost perfect. Almost perfect. And even though our accuracy is lower, it's not a problem. I mean, it's very high still. So, I think that concludes today's video. If you liked it, make sure to subscribe and hit the bell for more content. And leave any comments in the section below with any suggestions you have for the channel. I'll see you guys tomorrow. Have a fantastic day.